बर्नौलीज प्रिंसिपल हम लोग वही करेंगे। ठीक है, ओके। तो what is Bernoulli principle? It gives the relation between pressure, velocity and height of the liquid. Pressure at any point, velocity at that point, and the height of the liquid at that point. It is basically it comes basically from conservation of energy. ठीक है, Bernoulli equation comes from the conservation of energy. ठीक है, whatever energy conservation you know, the kinetic energy, potential energy, those things and work done, those things are solved and Bernoulli principle is formed. ठीक है, लिख लो इसके बारे में थोड़ा सा, फिर then we will do the derivation. Write it. Bernoulli's principle comes from conservation of energy. And gives a relation between velocity at a point, pressure at that point, and height of that point. ठीक है, तो कैसे ये चीज होता है, कैसे एनर्जी कंजर्वेशन आता है, देखते हैं। इजी एकदम, देखो अगर नहीं समझ में आएगा, स्कूल में कहीं हुआ होगा, देखना एकदम इजी है, तुरंत समझ, एक बार ध्यान दोगे थोड़ा सा समझ में आ जाएगा, और एक बार याद हो जाएगा ना, एक बार समझ जाओगे तो फिर दोबारा आराम से लिख दोगे। ऐसे बुक में खुद से पढ़ने जाओगे तो बड़ा कॉम्प्लेक्स लगता है कि क्या क्या कितना सारा टर्म्स दिया हुआ है, एकदम सिंपल है। मैं बता रहा हूँ, सपोज वी हैव ए ट्यूब ऑफ फ्लो लाइक दिस, ऐसे, ठीक है, and we will consider the two parts, one at this point, other at this point, and we will write different values. Suppose this part is at height h1 from the ground, this part is at height h2 from the ground. First we have written height, then we will write the area of cross section A1 at this point, then we will write area of cross section A2 at other point for this tube of flow. For tube of flow, ठीक है, लिखते जाओ साथ, H is for height, A for cross section area, now water is entering at speed v1 at this point, so v is speed of water or liquid, and other side it is exiting at v2 speed, ठीक है, then rho will be common, that is density, then we will assume pressure at this point P1 and pressure at other point P2. P is pressure, ठीक है, okay. Now we will try to write the energy equation. We will try to write the energy. How much work will be the work energy theorem? From work energy theorem we will write. From work energy theorem, do we know that total work done on a system is equal to change of potential energy plus change of kinetic energy. So from work energy theorem, we know that work done on a system is equal to change of potential energy plus change of kinetic energy. ठीक है? एक चीज और यहाँ पर हम लोग लेंगे. Suppose we consider for a small time dt, कोई भी delta t कोई भी for small time delta t, suppose x1 amount has entered and correspondingly this side x2 amount has exited. x1 लेंथ है, x1 लेंथ मैं बता रहा हूँ, अमाउंट सेम होगा. हाँ ठीक है. x1 is not amount, length. x1 is length in the tube which it has entered. Okay. x1 is length. So we can write the area A1 into x1, the volume which has entered, equal to A2 into x2 from equation of continuity. And the same thing we can also write A1 V1 equal to A2 V2. Okay, these things we can write. Okay, now we will write the work done on this system. So what will be work done? What are the different forces acting on this system? Water is moving, and on this tube of flow, the work done on this tube of flow, if we see, a pressure is acting from that side, and pressure is acting and it is moving the whole liquid by a distance x1. Are you getting? This liquid is experiencing a pressure from the other parts of liquid, and it is getting worked by a value P1 into area 1, that is force into displacement. Will it be the work done on the liquid from first side? Pressure into area, because pressure will act from the other parts of liquid. So pressure into area is force into displacement. And if we look at the second side, this side, this tube is working on the other parts of liquid. The work is not being done on the tube, but tube is working on the other parts of liquid. So we can write with minus sign. Here the tube is doing work on the other part. So we will write P2 A2 X2. This is the work done. Is it clear? This is the work done. The work done on the tube, work done by the tube. Okay, next. Potential energy. What is change in potential energy if that amount enters and this amount exits? You can see this part, the inner part remains same. The inner part of the tube remains same. What is the change? This much amount has decreased from here, and the same amount has appeared on other side. That can be said. Actually, whole tube has shifted by a small amount. So we have to add the potential change of this part by a small amount, this part by a small amount, this part. Every part we have to add. But since we know that from here to here it is same, we can directly write whatever entered from this side and whatever exited from other side. We can compare that energy and we can write as a change of potential energy. So the liquid A1 X1, that is volume entering into rho, the mass, and this mass has been elevated by how much amount? H1 minus H2 minus H1. Can we write like this? And A1 X1 is same as A2 X2. A1 X1 is same as A2 X2. Okay, so that is not going to make any difference. And then we will add kinetic energy. So kinetic energy at that place, A1 x1 rho, that is mass of the object or the water which has entered. Half mv square is the kinetic energy, so half m v1 square. Or change of kinetic energy we have to write now. So final minus initial. A1 x1 is the volume, that is same, so we can take them as same. अच्छा रहेगा ना कि हम लोग इसको ऐसे लिखते हैं. We will take it as the mass entering m के फॉर्म में लिखे, ज़्यादा अच्छा रहेगा. It will be less confusing if you write like this m. ठीक है? So write it better one, because one or two में फिर confusion हो जाएगा. Write it as m. That mass which is entering from the one side. Mass entering. In this small time dt, and m v2 square minus m v1 square. Can we write like this? ठीक है, लिख सकते हैं. अब देखो, is it clear up to here? Okay, now a1 x1, can we write this a1 x1? This is volume entering, so this also needs to be converted into mass. We will write everything in terms of mass. So P1. Now can we write this volume as mass by density minus P2 mass by density equal to mass H2 minus mass H1 minus plus half mass V2 square minus half mass V1 square. So mass will get cancelled in all the terms, and we will have P1 minus P2 equal to rho H2 minus rho H1 plus half rho V2 square minus half rho V1 square. And now take all the quantities which have subscript 1 on the one side and which have subscript 2 on the other side. So on one side we will have P1 plus this term.
सर चलो A2
है क्या? वो G भी था ना यहाँ पर, वो G छूट गया. G नहीं है. So write it rho G H1 and then take this one plus half rho V1 square on one side.
सर A1 x1 को डायरेक्ट m ही ना डालेंगे, मतलब m ये थे ना
कौन सा?
A1 x1 को, तो क्या है m by
rho ये है ना, तो वॉल्यूम है ना, मास बाय, इसको ऐसे रखना है, इसको डेंसिटी से मल्टीप्लाई कर दो, मास में, ठीक है, मास है A1 तो वॉल्यूम है वो तो. ओके, ऐसे लिख सकते हैं. मेन थिंग देखो इसमें क्या है ना कि ऐसे लिख के उसके बाद सारे चीजों को जो है पहले प्रेशर लिख दिया, ठीक है, वर्क लिख दिया. अब क्या करना है कि मास और डेंसिटी के टर्म्स में सारे को लाना है. ये क्या होगा, दूसरे साइड क्या हो जाएगा, P2 प्लस रो जी H2 प्लस हाफ रो V2 स्क्वायर. ठीक है, so this is the final expression which we have got.
तो सर फिर वहाँ तो m by rho हो जाएगा ना,
कहाँ पर?
जहाँ पर आप डायरेक्टली A1 x1 की जगह पे m ले लिया था, वहाँ पर उस साइड इक्वेशन का mg h2 h1 वाला भी.
क्या था एक्सप्रेशन? ये सही है ना, ये तो वॉल्यूम मास बाय ये करनी है. ठीक है, ओके. ये क्या हो जाएगा, देखो इसका मतलब क्या निकल रहा है, व्हाट दिस एक्सप्रेशन मींस दिस थ्री टर्म्स, इफ यू टेक सम ऑफ दिस थ्री टर्म्स it remains constant at these 2 points. So we have taken any 2 points arbitrarily we have taken. So this quantity remains constant for any flow. ठीक है? This is pressure plus rho gh plus half rho v square. This is pressure rho gh half rho v square. This corresponds to pressure energy बोलते हैं इसको. This corresponds to potential energy and this corresponds to kinetic energy. Pressure energy is nothing but it is work, and this you are already knowing. This is kinetic energy per unit volume, because generally what is kinetic energy? Half mv square, and here are having half rho v square. So this is kinetic energy per unit volume, kinetic energy density you can say. This is kinetic energy density. This is what? Potential energy density, and this is called pressure energy density, but you can understand it at a work. This term has came from the work. You can see this has came from work. So pressure energy density. Okay. So we write in a compact form, we write it like this. P plus rho g h plus half rho v square equal to constant. ठीक है? ये चीज हम लोग लिखते हैं किसी भी फ्लो. दिस इज फॉर नॉलेज. तो इसे क्या क्या कंक्लूजन निकाल सकते हैं? What different conclusions we can draw from this? In any horizontal flow, if we consider, h will remain what? Constant. Then if velocity is more, then pressure will be less, because their summations are fixed, okay, constant. So in any horizontal flow, if you see, what will be change in pressure? If velocity is increased, pressure will be less. कुछ डाउट है किसी को? बोलो, कुछ डाउट है? बोलो, डाउट है तो पूछो. अमरदीप, डाउट है कुछ? उसका कॉपी देख रहा है. Okay. We can analyze this in different situations. If we have a horizontal flow, the h will be same throughout. Then increase of velocity means decrease of pressure, and that's why when there is cyclone, we have very low pressure in that region, nearby region. In any place, if you have very high velocity, the pressure in that region is very less. Okay? And suppose you are standing at a platform and a train is crossing at the platform, and you are standing at some distance. The train will move, suppose it will pass with a very high speed, and the nearby air will also move with very high speed. You may stand at some distance, maintaining some distance, but it can attract you from a distance also, if the distance is not sufficiently large, because of this principle. The velocity is small in that region nearby that train, and due to the high velocity, the pressure in that region is less, and it can attract the objects which are very near to the track. Yeah. Apart from various other applications are there. So write different applications of Bernoulli principle. Different applications of Bernoulli principle. कहीं भी प्रेशर कम होता है ना, तो हाई प्रेशर से चीजों को खींचता है वो. If pressure is less at any point, it will try to attract other objects from the other places to that point.
तो वहाँ पर तो वेलोसिटी हाई हो गया ना?
हाँ, वेलोसिटी हाई है, वेलोसिटी हाई होना एक चीज हुआ, बट प्रेशर कम हो जाता है।
क्यों?
ये सब क्यों, तो यही चीज हम लोग फार्मूला आगे तो डेराइव किए क्यों, ठीक है, डेराइव किया क्यों? हाँ, एक्चुअली प्रेशर, हाँ ये चीज कांस्टेंट रखने के लिए होता है। प्रेशर जहाँ पर हाई वेलोसिटी होगा वहाँ प्रेशर कम होगा। Now we will discuss various applications. It will be more clear. The first thing we will discuss the hydrostatic pressure, जो already हम लोग discuss कर चुके हैं. Hydrostatic pressure or static liquid. How do we apply the Bernoulli principle for static liquid? So for static liquid, the V will be what? 0. So P plus rho GH. So for static liquid, the first thing we will write is static liquid. क्या होगा बताओ? P plus rho GH is constant or P1 plus rho GH1 equal to P2 plus rho GH2 or P1 minus P2 equal to rho GH2 minus H1 or delta P is minus rho G delta H. These are the things which we have already studied for hydrostatics. Okay. Second, we will see Torricelli's theorem. What is this theorem says? If we have a liquid and it is filled up to height h, okay, then the water which will come out from a hole at a depth h from the top surface is having velocity under root 2gh. Same as an object which is falling from height h. We know from kinematics as well as from work energy power chapter, if an object falls from height h, how much velocity it acquires? Under root 2gh. Under root 2gh, ठीक है, gh नहीं, under root 2gh. तो that is the thing also coming from the Bernoulli principle. So how do we write this formula? This is the Torricelli's theorem. So देखो, if we take a point here, and we take another point here, we assume that this surface is very large in size. Actually क्या होता है ना कि surface अगर large नहीं हुआ वो भी हम लोग करके देखेंगे. If it is large, if area is large, then with change of this, when the water comes out from this part, there will be a very negligible amount of change in this height. So we can neglect this velocity in that case. That's why we have taken large area. Although in actual practice, if we have some velocity here, we will have corresponding velocity here also. But this will be very small, so we can neglect it. Now we will apply that theorem. So pressure at this point is how much? P naught, atmospheric pressure. At this point, atmospheric pressure plus rho g h. So h height, rho g h plus velocity will be 0. Because of large area, we can neglect the velocity. This will be equal to all the values calculated at the other point. At this point, when the liquid comes out, again pressure will be P naught, the atmospheric pressure. We are not calculating here. We are calculating the just of velocity just at the nozzle. ठीक है, जस्ट आउटसाइड. So P naught plus, it was the pressure plus height will be 0. If we measure the height from here, the height taken at this point will be 0, and the velocity will be v. So we can write half rho v square. So we can see ठीक है, this we can write. But if area is not very large, if it is comparable to the whole area, then we should include the area here also, the velocity of that other part also. Okay, so we can write there also, if the top area is not very large, if top area is not very large, then what we should write? P naught plus rho gh plus velocity at top. मान लो यहाँ पर 1 लिखते हैं, यहाँ पर 2 लिखते हैं. So we can write half rho v1 square equal to P naught plus rho g, ये तो 0 हो जाएगा, half rho v2 square. And suppose we take this area A2, और ऐसे नहीं लिखो, A2 मत लिखो, इसको small a and large a. Small a and large a. Then can we relate these two velocities from equation of continuity? Can we write a v2 equal to capital A v1? Can we write like this? Now we will solve it like this. Rho h plus half rho को तो हटा ही दो, half v1. So we have to find finally v2 at this point. So v1 has to be converted into v2. So it will be a v2 by capital A equal to इसको टफ लग रहा है, टफ तो नहीं है लेकिन बहुत ज्यादा होगा, इसमें जा सकता है. और तो कुछ नहीं है, तो क्या करेंगे बताओ? v2 equal to 2gh, this will come this side, and 1 minus a square by capital A square here. ठीक है, we can write like this. रो खत्म, अच्छा रो नहीं खत्म, कैंसिल हो गई. Okay, if this a was very small as compared to capital A, then this term was negligible and we had neglected. That was the last case. But if these two are comparable, then we have to use this formula. This is Torricelli's theorem. ठीक है. समझ में आया? ठीक है. तो इसमें बहुत छोटा छोटा क्वेश्चन रहता है, सीधे वैल्यू दिया रहेगा, निकालना रहेगा, हाइट दिया रहेगा, कितना वेलोसिटी से पानी गिर रहा है, बस ऐसा ऐसा क्वेश्चन रहता है. बहुत टफ क्वेश्चन इसमें नहीं आता.